cost of 5. Self-induction and mutual induction. The number of interlinkages of an electric circuit with the lines of magnetic force of the flux produced by unit current in the circuit is called the inductance of the circuit. The number of interlinkages of an electric circuit with the lines of magnetic force of the flux produced by unit current in a second electric circuit is called the mutual inductance of the second upon the first circuit. It is equal to the mutual inductance of the first upon the second circuit, as will be seen, and thus called the mutual inductance between the two circuits. The number of interlinkages of an electric circuit with the lines of magnetic force of the flux produced by unit current in this circuit and not interlinked with a second circuit is called the self-inductance of the circuit. If I equals the current in a circuit of n turns, phi equals the flux produced thereby, and interlinked with the circuit, n times phi is the total number of interlinkages, and L equals n times phi divided by I, the inductance of the circuit. If phi is proportional to the current I and the number of turns n, phi equals n times I divided by rho, and L equals n squared divided by rho. Rho is called the reluctance, and n times I the magnetomotive force of the magnetic circuit. The reluctance rho has in magnetic circuits the same position as the resistance R in the electric circuit. The reluctance rho, and thus the inductance, is constant only in circuits containing no magnetic materials, such as iron. If ρ1 is the reluctance of a magnetic circuit interlinked with two electric circuits of N1 and N2 turns respectively, the flux produced by unit current in the first circuit and interlinked with the second circuit is N1 divided by ρ1, and the mutual inductance of the first upon the second circuit is M equals N1 times N2 divided by ρ1, that is, equal to the mutual inductance of the second circuit upon the first circuit, as stated above. If ρ1 equals rho, that is, no flux passes between the two circuits, and L1 equals the inductance of the first circuit, L2 equals the inductance of the second circuit, and M equals the mutual inductance, then M squared equals L1 times L2. If ρ1 is larger than rho, that is, if flux passes between the two circuits, then M squared is less than L1 times L2. In this case, the total flux produced by the first circuit consists of a part interlinked with the second circuit also, the mutual inductance, and a part passing between the two circuits, that is, interlinked with the first circuit only, its self-inductance. Thus, if L1 and L2 are the inductances of the two circuits, L1 divided by N1 and L2 divided by N2 represent the total flux produced by unit current in the first and second circuits, respectively. Of the flux L1 divided by N1, a part S1 divided by N1 is interlinked with the first circuit only, and S1 is called its self-inductance. The part M divided by N2 is interlinked with the second circuit also, where M equals the mutual inductance. Thus, L1 divided by N1 equals S1 divided by N1 plus M divided by N2. If minus L1 and L2 equal the inductances, A1 and A2 equal the self-inductances, M equals the mutual inductance of two circuits with N1 and N2 turns, we have the following equations. The practical unit of inductance is 10 to the 9th times the absolute unit, or 10 to the 8th times the number of interlinkages per ampere, since 1 ampere equals 0.1 unit current and is called the Henry. 1,000th of a Henry is called the millihenry, abbreviated as mH. The number of interlinkages for a current of I amperes in a circuit with L Henry inductance is I times L times 10 to the 8th lines of force turns. Thus, the EMF induced by a change of current, dI in time dt, is E equals negative dI divided by dt times L times 10 to the 8th absolute units, which equals negative dI divided by dt times L volts. A change of current of 1 ampere per second in a circuit with 1 Henry inductance induces 1 volt.
Examples 1.
What is the inductance of the field of a 20-pole alternator? If the 20 field spools are connected in series, each spool contains 616 turns, and 6.95 amperes produces 6.4 megalines per pole. The total number of turns of all 20 spools is 20 times 616, which equals 12,320. Each turn is interlinked with 6.4 times 10 to the sixth lines of force. Thus, the total number of interlinkages at 6.95 amperes is 12,320 times 6.4 times 10 to the sixth, which equals 78 times 10 to the ninth. 6.95 amperes equals 0.695 absolute units. Hence, the number of interlinkages per unit current, or the inductance, is 78 times 10 to the ninth divided by 0.695, which equals 112 times 10 to the ninth, or 112 henries. 2. What is the mutual inductance between an alternating transmission line and a telephone wire carried for 10 miles below, 1.20 meters distant from one conductor and 1.50 meters distant from the other conductor of the alternating line? What is the EMF induced in the telephone wire if the alternating circuit carries 100 amperes at 60 cycles? The mutual inductance between the telephone wire and the alternating line is the magnetic flux produced by unit current in the telephone wire and interlinked with the alternating circuit. This includes the part of the magnetic flux produced by unit current in the telephone wire that passes between the distances of 1.20 meters and 1.50 meters. At a distance x from the telephone wire, the length of the magnetic circuit is 2 times pi times x. The magnetizing force is F equals I divided by 2 times pi times x, where I is the current in the telephone wire in amperes. The field intensity is H equals 0.4 times pi times F, which equals 0.2 times I divided by x. The flux in the zone dx is d phi equals 0.2 times I times L divided by x times dx. For a length L of 10 miles, which equals 16,100 centimeters, phi equals the integral from 120 to 150 of 0.2 times I times L divided by x times dx, which equals 322 times 10 to the third times I times the natural logarithm of 150 divided by 120, which equals 72 times I times 10 to the third. 72 times I times 10 to the eighth interlinkages. Hence, for I equals 10, or 1 absolute unit, M equals 72 times 10 to the fourth absolute units, which equals 72 times 10 to the minus fifth henries, or 0.72 millihenries. 100 amperes effective, or 141.4 amperes maximum, equals 14.14 absolute units of current in the transmission line. This produces a maximum flux interlinked with the telephone line of 14.14 times 0.72 times 10 to the minus 3 times 10 to the ninth, which equals 10.2 megalines. Thus, the EMF induced at 60 cycles is E equals 4.4 times 0.6 times 10.2, which equals 27.3 volts effective. This video is based on the convention used by Charles Steinmetz. Explanation of terms like unit current can be found in the previous video, linked in the description. 6. Self-induction of continuous current circuits. Self-induction manifests itself in continuous current circuits only during starting, stopping, or generally changing the current. Starting of current if R is the resistance, L is the inductance of the circuit, E is the continuous electromotive force impressed upon the circuit, minus I is the current in the circuit at time t after impressing the electromotive force E, and dI is the increase of current during the time moment dt, then the increase of magnetic interlinkages during the time dt is L times di. The electromotive force induced thereby is E1 equal to negative L times dt, negative because it is opposite to the impressed electromotive force as its cause by Lenz's law. Thus, the electromotive force acting in this moment upon the circuit is E plus E1 equal to E minus L times di divided by dt. The equation for the total electromotive force acting in the circuit at any moment is E plus E1 equals E minus L times di divided by dt. Thus, the current at time t, denoted as I, is given by I equals the quantity E plus E1 divided by R, which equals the quantity E minus L times di divided by t, all divided by R. Negative L divided by R times dt equals di divided by the quantity I minus E divided by R. The integral of this is negative R times dt divided by L equals the natural logarithm of the quantity I minus E divided by R minus the natural logarithm of C, where the natural logarithm of C represents the integration constant. The current I is given by I equals C times e to the power of negative R times T divided by L, all multiplied by R. At time t equals 0, the current I equals 0. Thus, C equals E divided by R. Substituting this value of C into the equation for I gives I equals E divided by R times the quantity 1 minus e to the power of negative R times T divided by L. This equation gives the current at any time t. The electromotive force of self-induction is EI equals I times R minus E, which equals negative E times e to the power of negative R times T divided by L. As time t approaches infinity, I equals E divided by R, and EI equals 0. Substituting these values, I equals E divided by R times the quantity 1 minus e to the power of negative R times T divided by L, and EI equals negative R times I0 times e to the power of negative R times T divided by L. The expression L divided by R is called the time constant of the circuit. Substituting into the foregoing equation, we have I equals E divided by R times the quantity 1 minus e to the power of negative R times T divided by L, and EI equals negative E times e to the power of negative R times T divided by L. At time t equals L divided by R, the time constant of the circuit, I equals E divided by R times the quantity 1 minus e to the power of negative 1, and EI equals negative E times e to the power of negative 1. Substituting the value of e to the power of negative 1 equals 0.368, we find I equals E divided by R times the quantity 1 minus 0.368, which equals 0.632 times E divided by R, and EI equals negative E times 0.368, which equals negative 0.368 times E. Thus, at time t equals L divided by R, the current is I equals 0.632 times E divided by R, and the electromotive force of self-induction is EI equals negative 0.368 times E. In the stopping of current, consider a circuit with inductance L and resistance R, where a current I0 equals E divided by R is produced by the impressed electromotive force E. Let this electromotive force E be withdrawn and the circuit be closed by a resistance R1. Let the current be I at time t after the withdrawal of the electromotive force E, and let the change of current during the time moment dt be di. Since di is negative, as the current decreases, the decrease of magnetic interlinkages during the moment dt is L times di. The electromotive force induced thereby is EI equals negative L times di divided by dt, negative because di is negative, and EI must be positive or in the same direction as E to maintain the current or oppose its decrease as the cause. The current is then EI equals the quantity R plus R 1 times I, or negative L times di divided by dt equals the quantity R plus R 1 times I. Transposing, we get di divided by I equals negative the R plus R1 divided by L times dt. The integral of this is the integral of di divided by I equals negative the quantity R plus R1 divided by L times the integral of dt, or the natural logarithm of I equals negative the quantity R plus R1 divided by L times t minus the natural logarithm of C, where negative the natural logarithm of C is the integration constant. This reduces to I equals C times e to the power of negative the quantity R plus R1 times t divided by L, where for t equals 0, I equals I0 equals E divided by the quantity R plus R1, and thus C equals E divided by the quantity R plus R1. Substituting this value of C, we have I equals E divided by the quantity R plus R1 times e to the power of negative the quantity R plus R1 times t divided by L, which represents the current at time t. The electromotive force induced is given by EI equals I times the quantity R plus R1, which equals E times e to the power of negative the quantity R plus R1 times t divided by L. Substituting I0 equals E divided by the quantity R plus R1, we have I equals I0 times e to the power of negative the quantity R plus R1 times t divided by L, and EI equals I0 times the quantity R plus R1 times e to the power of negative the quantity R plus R1 times t divided by L. At t equals 0, I equals I0 equals E divided by the quantity R plus R1, and the electromotive force of self-induction is EI equals E. That is, The induced electromotive force is increased over the previously impressed electromotive force in the same ratio as the resistance is increased. When R1 equals 0, that is, when in withdrawing the impressed electromotive force E, the circuit is short-circuited. I equals E divided by R times e to the power of negative R times T divided by L, which equals I0 times e to the power of negative R times T divided by L, representing the current, and EI equals E times e to the power of negative R times T divided by L, which equals I0 times R times e to the power of negative R times T divided by L, representing the induced electromotive force. In this case, at T equals 0, EI equals E, that is, the electromotive force does not rise. In the case R equals infinity, that is, if in withdrawing the electromotive force E, the circuit is broken, we have at T equals 0, EI equals infinity, that is, the electromotive force rises infinitely. The greater R1, the higher the induced electromotive force EI. However, the faster E and I decrease. If R1 equals R, we have at T equals 0, EI1 equals 2 times E and I equals I0, and EI1 minus I0 times R equals E. That is, if the external resistance R1 equals the internal resistance R, in the moment of withdrawal of electromotive force E, the terminal voltage is E. The effect of the electromotive force of self-induction in stopping the current at the time t is I times EI equals I0 squared times the quantity R plus R1 times e to the power of negative 2 times the quantity R plus R1 times T divided by L. Thus, the total energy of the induced electromotive force is W equals the integral from 0 to infinity of I times EI with respect to t, which becomes W equals I0 squared times the quantity R plus R1 multiplied by the expression e to the power of negative 2 times the quantity R plus R1 times t divided by L, evaluated between 0 and infinity, multiplied by negative L divided by 2 times the quantity R plus R1. Evaluating the integral, W equals I0 squared times L divided by 2, which is the energy stored as magnetism in a circuit of current I0 and self-inductance L. This energy is independent of both the resistance R of the circuit and the resistance R1 inserted in breaking the circuit. This energy must be expended in stopping the current.